Okay, in this video, I want to talk about gravity from a little bit different perspective than how we did back when we were talking about projectiles and things like that. So we've talked about how F equals mg gives a different value from F equals mv squared over r for the moon traveling around the Earth. And since we observed that the moon really does travel in approximate circles around the Earth, the fact that these two equations don't match up, it is implying that F equals mg is not accurate. The circular motion equation definitely is. So I don't want to get too far into the history, but I would like to give you a little bit of background on this. Civilizations all around the world had recorded the apparent circular motion of stars in the sky. This is especially easy to see if you are up at night in an area that is not well lit. So like in ancient times, most people would have had an opportunity to do this, especially in farther northern or southern climates where the days in the winter are very long and there's nothing to do. You would see that the constellations change their orientation, and again, every civilization had figured out that they pretty much all go in a circular path around the sky. Astronomers in many cultures had also carefully documented the motion of 7 objects that follow different rules from the stars. That is the sun, the moon, and what we now know as Mercury, Venus, Mars, Jupiter, and Saturn. You can see all of those with the naked eye. Those objects do something other than the pattern that is on the screen right here. Those patterns are more complicated than what you see here, but they're still predictable within a system that supports the idea that they orbit the Earth and that they're possibly on some kind of track in the sky. And that's what most ancient cultures believed. The idea of a heliocentric universe, where the planets all orbit the sun, had been suggested by astronomers in Greece and in India and in Persia and possibly other places. Credit is usually given to Copernicus in Poland in Eastern Europe, largely because he published a book using the newly invented Gutenberg printing press, and that allowed his ideas to be distributed widely and then built upon. Just a few generations after Copernicus came Galileo, and Galileo began a lot of very important work for laying the foundations of what we consider physics and really all modern science today. He established the independence of motion in the x, y, and z directions. He established that objects of different masses will fall at the same rate. The conversation we had earlier in the semester about objects going down a ramp. Galileo is also the one who established the rules of parabolic projectile motion and the concept of inertia. And then one of the other things he did was he improved on the telescope, which is a relatively recent invention. And as far as we know, he's the first person to use it in astronomy. This is a picture of Galileo's telescope. He made sketches of the moon's surface showing that it is pretty clear that these are craters and mountains. That's not very obvious when you look at the pattern of the moon's surface with the naked eye. But through a telescope, even a not very strong one, you can get a pretty good idea that those really are craters and those really are mountains. He also documented that Venus has phases like the moon does, crescent and half and full and things like that. He also discovered that there are moons orbiting Jupiter, and that may have been the biggest deal, because by the time someone like Isaac Newton came along, not long after Galileo, there was this question of whether or not the objects in the heavens follow the same laws of motion as the objects on Earth do. That's not something that would have been considered a very reasonable question much before Galileo. But having built on certain technologies like the telescope, these people were able to also build on each other's knowledge. And so by the time Isaac Newton comes around, he's trying to study what is it that is a force on the moon as the moon travels in circles around the Earth. What kind of invisible force could make an object be drawn towards the Earth? What kind of invisible force pulls things towards the planet? Hey, I know. The story that an apple fell and hit him on the head is not true, but in later years, Newton said that the idea that an apple falling and the moon going in circles around the Earth, that these could be possibly due to the exact same force, that idea came to him when he was sitting in his mother's apple orchard and saw an apple falling while he was thinking about the moon. So there's some connection there at least. After a lot of extensive calculations about the speeds and the distances between the various planets and the sun and of Jupiter's moons going around Jupiter, he derived this equation, which we now know as the universal gravitation equation. So we need to make sure that we know how to use this universal gravitation equation. And what it says is there's a force of gravitational attraction between any two masses, and that gravitational attraction is proportional to each of the two masses, so mass 1 times mass 2. Inversely proportional to the distance squared, so that r squared, some textbooks and websites will refer to it as a d squared. That's just the distance from the center of mass of the one object to the center of mass of the other object. And capital G is not some mystical term, sometimes referred to as the gravitational constant of the universe, but what it really is a way to make this calculation give us units that make sense. The main point here is if mass 1 is bigger, the force of gravity is bigger. If mass 2 is bigger, the force of gravity is bigger. And the force of gravity between any two objects will be greatest when they are closest together. As they get farther and farther apart, that r value gets bigger, but that r value, which then gets squared, is in the denominator. The way that we will want to use this equation is like this. If you get asked how strong is the gravitational force between a 1 kilogram object and another 1 kilogram object, and they're near each other on the lab bench, you're going to come up with a very, very, very small force. In fact, we may put that in a future video now that I've mentioned it. But how about how strong is the gravitational force between a 1 kilogram object and the planet Earth while the object is sitting on the planet's surface? So now you need to know the mass of the 1 kilogram object is 1 kilogram. You need to know the mass of the Earth. So that would either be given or you would be allowed to look it up in a situation where you could be expected to do this calculation. The gravitational constant, G, is the same anywhere in the universe as far as we're concerned, and that would be given. Notice the units in that. It's units of meters cubed, kilograms to the -1, seconds to the -1. If you recall, when you raise something to the minus power, that means it's in the denominator. So sometimes this is shown as 6.67 times 10 to the -11th meters cubed per kilogram second. Doesn't really matter which way you write it. You do want your masses in kilograms and your distances in meters, or else you will not have force come out in newtons. You need to know the radius of the Earth in order to solve this problem. And the reason you need to know the radius of the Earth is if a 1 kilogram object is sitting on the surface of the Earth, that means it is in contact with the Earth. But how far away is it from the planet Earth? We measure the distance from the center of one object to the center of the other object. So right now, sitting on the surface of the planet, you're about 6,371 kilometers away from the center of the planet, and that was the value that you would need to use to plug it into the universal gravitation equation. And again, that's a value that you would either be given or you could look up in any given situation. The way you use the equation is just this. The force of gravity is equal to the gravitational constant G times the mass of the Earth times the mass of the object that we're talking about, divided by r squared, where r is the distance from the Earth's center to the center of the object. So you plug these numbers into this equation. This is where it becomes really important to have a scientific calculator or a graphing calculator, or to be really adept at doing some calculations by hand using scientific notation. So if you don't have a calculator that does scientific notation really well, doing it by hand is actually pretty easy, but you may want to refresh yourself on how to. Also notice I've taken that distance, which when I looked it up was given in kilometers, and I'm going to have to turn that into the kilometers into a times 10 to the third, so that my units of distance are meters when I put it into the equation. And so we wind up with 9.81 newtons of force between the Earth and a 1 kilogram object if that 1 kilogram object is on the surface of the planet. On the surface of the planet, F equals m times lowercase g works just fine. Gives you the exact same equation as universal gravity. The catch is if you're not on the surface of the planet, F equals m times lowercase g no longer works. However, this new equation works no matter how far away you are. It's called universal gravitation because technically at any distance, even on the other side of the universe, you could find that distance. Well, if you could find that distance, you could put that into this equation and you still wouldn't technically ever calculate zero gravity between two objects that have mass. I'd like to do a quick example problem, even without getting any coffee, just to talk about, here's this made-up planet, and made-up mass for this planet is 5.8 times 10 to the 25th kilograms, and I'm going to make up a second planet, and its mass is 7.98 times 10 to the 23rd kilograms, and I'm going to say, how do we determine the force of attraction between them if the distance is given? That distance is actually a really large number for the perspective of things on Earth, but it's pretty reasonable for things like how far apart are planets in our solar system. Why you would ever want to know this isn't the reason why we're doing this example. I'll show you in just a second why we're doing this example. This is just a matter of taking these numbers and putting them into our given equation. So you would have to know what the equation is or where to find it. Then you would have to know that the mass of your ringed planet and the mass of your yellow planet get multiplied by each other. They get multiplied by g, which is a value that you can look up, and they get divided by that distance squared, being careful to change kilometers to meters again. And so you get some value, 1.0 times 10 to the 16th newtons, which is a really, really large force. There's 2 points I want to make. Number one, if you were to try to calculate the acceleration these two objects experience as they pull each other with this amount of force, you would very quickly find out why Newton went ahead and invented calculus. You see, as soon as these two objects start accelerating toward each other, they start moving toward each other, so the distance between them changes, which means that the force between them, which depends on the distance, also changes. As soon as they start moving toward each other, they're closer together, so the force between them is stronger. So the acceleration is stronger. So they move toward each other faster. So the distance between them is less. So the force between them is greater, etc. The reason this doesn't actually cause planets to crash into each other is the subject of our next video, which will be about orbits. But for this one, we've got this 1.0 times 10 to the 16th newtons. The other thing I really wanted to point out is, what happens if I take that exact same scenario and I tell you that I'm going to move the little planet to a distance exactly double its original distance? You could go through and set up the equation the exact same as how you did before and put a 2 times the original distance in the denominator. But what's going to happen with that 2 in the denominator? That 2 times the distance means that there is a times 2 in the denominator, and that times 2 actually gets squared. So whatever I'm doing to one side of the equation, I have to do to the other side of the equation. And I could do that in a more straightforward shortcut way like this. The force of gravity between them in the original setup is now going to be multiplied by 1 over 2 squared, because we're doubling the distance and because the distance gets squared by the equation. So it just becomes the original force divided by 2 squared. It's 1/4 of its original value, 2.55 times 10 to the 15th newtons. What if I take that original setup and I triple the original distance, so that these two objects are now 3 times farther apart than they were? The same principle applies. I'm now going to triple the distance, but that tripling gets squared in the denominator. So on the other side of the equation, I need to take that original force of gravity and multiply it by 1 over 3 squared also. So if you triple the distance, you wind up with a force that is 1/9 of what it was. If you take the original distance and make it 10 times bigger, then the force then becomes 1 over 10 squared of what it originally had been, or 1% of what it originally had been. The reason I'm pointing this out is that there are several things in nature that behave this way. The gravitational force of attraction is one thing. In Physics 150, you'll talk about electrostatic attraction and repulsion, and it works on the same principle. Slightly different numbers, and it's slightly different objects that it applies to, but still this idea that the force is stronger when you're closer and weaker when you move apart, and exactly in this manner, you'll find comes up again in Physics 150. This is also how things like how bright a light or how bright a star looks. It follows this exact same formula. If you are 10 times farther away from the sun, then the sun would look about 1% as bright as we currently see it. So sort of an underlying principle to a lot of physics. I'd like to do one more example problem or rather a sort of application, and that is, how do you calculate the gravitational field strength on any given planet? It's 9.8 newtons per kilogram here on Earth, so if you drop an object near the surface of the planet, it will fall at 9.8 meters per second. How do we know how strong that is on the moon, or on Mars, or on Jupiter? We have all these values, like you can go look it up on the NASA website, but like, how does NASA know this? And the way they know this is this: the force of gravity is G times the mass of the planet times the mass of some object that you're talking about on the planet, divided by the radius of the planet squared. But if you're near the planet's surface, then the force of gravity for that object is the mass of the object times G of the planet. And since these are both, as long as you're near the surface of the planet, these are both valid expressions for the force of gravity between some object and the planet, you could set those expressions equal to each other. G times the mass of the planet, capital G, let me be clear about that. Capital G times the mass of the planet times the mass of the object, whatever the object is, divided by the radius of the planet squared, equals the mass of that object, whatever that object is, times G of the planet. Since the mass of that object, whatever that object is, appears on both sides of the equation, it doesn't have to appear on either side of the equation at all. We can divide it right out. And we now have an expression that says that the gravitational field strength on any planet, and therefore the acceleration due to gravity for any object that you drop on that planet or moon, is equal to capital G, which is a constant, times the mass of that planet or moon or whatever, divided by the radius of that planet or moon or whatever squared. So the way you would use that is something like this. What if I wanted to know what the gravitational field strength is on Mars, and I gave you this information right here? The mass of Mars is given and the radius of Mars is given. The gravitational field strength, therefore, on Mars is the, I'm just switching the equation around here so it looks better like this. Universal gravitational constant of 6.67 times 10 to the minus 11th meters cubed per kilogram second times the 6.42 times 10 to the 23rd kilograms that Mars is, divided by the radius of Mars, which is 3,389 times 10 to the third meters, and you have to make sure you square that. And when I put all that in my calculator, I get that the gravitational field strength on Mars is 3.7 meters per second, which is what NASA says. So I'm going to take that as a check on my work when I agree with NASA. All right, that's it for this video. In the next video, we'll talk a little bit about how gravity causes orbits, and we'll throw a couple examples into that.